what is called the Aharonov bomb effect, which must be well known to audience here. And this is a fascinating phenomenon when electrons can actually be physically influenced by magnetic fields without crossing the fields. So the underlying point is that a magnetic field has a vector potential which pervades all space, and that vector potential influences the quantum phase of the electron wave function. And because of that, you see quantum coherence. And that leads to observable phenomenon such as persistent current, persistent electric current. And that is happening in a circuit or an Aharonov bomb ring without any external electric field. It's not a superconductor, it's normal state electric current. And that's also related to diamagnetism. It's a very interesting situation in which a phenomenon like diamagnetic moment, which you can calculate from the equilibrium partition function, gets related to something like a transport property. Now, to study this phenomenon, you can set up a familiar tight binding model. If I use ever, I'll use the acronym TB. So you write down a Hamiltonian, which again is well known to the audience here. So suppose you have a term like summation over lattice sides. So we talk about weakly localized electrons in the lattice. So you have EL. I'll write it in this notation. Different people write it in different notations. And then you have summation over LJ, JLJ. And then you have this Aharonov bomb flux or the phase on the off-diagonal elements of this tight binding model, then you have this Hermitian adjunct. So what is this phase phi LJ? Phi LJ, you have the divide by the quantum magnetic flux, which occurs elsewhere, for instance, quantum Hall effect. And then you basically have the external magnetic field times half of an area vector that you can construct out of the, so okay, L and J, of the Lth and Jth sides, because this is the area vector. The magnetic field dotted to the area vector gives you the total magnetic flux. So, so therefore, now, so this is pure quantum mechanics, and you have quantum coherent effect. And so we'll solve this problem on a very simple situation. But what I want to talk about is what happens when you add noise. So that is the alibi for me to give this talk in the STATPHYS meeting. So add statistical noise onto this system. And the particular kind of noise that we will discuss is what is called a telegraph process. What is a telegraph process? You take a two-level jump process, and if you take one sample of f of t as a function of time, then f of t is a function that randomly jumps between the values +1 and -1, and it stays for, again, random durations, so there's the mean time between two such jumps that you can define. So what do you want to calculate? You want to calculate the persistent current. So how do you get the persistent current is what I will now discuss. So what you expect that if you have such a stochastic noise in the system, what you're trying to do is to model the effect of the environment on this quantum system. And so and the environment, therefore, would cause decoherence, and you would expect the persistent current to decay. And that's what we would like to calculate. We'd also like to see if we can calculate in closed form the decay rate of the persistent current. So I solved this problem. I must say that this is an outgrowth of an earlier collaboration on retrieval of quantum information in a qubit system despite noise. That work was done with Amnon Aharoni and Orion Tin-Ullman in Beersheba and Ben-Gurion University, and also Shmuel Gurevitz in the Weizmann. So what we do is we take a simple model where I can do all these calculations exactly. So you have a three-site mesoscopic ring. Is this Aharonov-Bohm rings on which the Aharonov-Bohm effect and quantum interference effects were first seen experimentally. So you assume that you now simplify your tight binding Hamiltonian on just a three-dot Aharonov-Bohm ring, where you have, let's say, this dot number 1, dot number 2 here, and dot number 3. And so you can actually, with the origin at the center of the circle, you have these vectors, so R1, R2, R3, and the triangle that you're considering is this one, so that's the shaded area. And it turns out that the diamagnetic moment, which you can actually calculate from the expectation value of the negative derivative of the partition function with respect to the magnetic field, is the average diamagnetic moment is actually given by, let's say, the bond current between the sites of the dots 1 and 2 divided by the quantum flux times the area of the triangle that I have just constructed out of these three sides. So that's the shaded area of this triangle. And the reason that it suffices to only consider, let's say, the current between the dot 1 and 2 is because of the particle number conservation. You have the current going in this loop, let's say from site 1 to 2, has to be the same as the current going from site 2 to site 3, as well as the current going from site 3 to site 1. And so because of this, it suffices to just consider, let's say, I12 because of this equality. So the simple model that we can solve exactly is the one which is called the symmetric ring model. So assume symmetry. And Krish, have you already raised your hand? Okay. So minus j to the I phi plus the Hermitian adjoint. Okay. Now, just write down its matrix form in this dot representation. This will turn out to be simply 0 e to the I phi, e to the minus I phi, e to the I phi, 0 e to the minus I phi, e to the I phi, e to the minus I phi. 0 is a 3 by 3 matrix. You can diagonalize it exactly, get the eigenvalues. The eigenvalues read like 2 cosine phi, lambda plus minus is minus, so this is minus cosine phi. And you have cosine phi plus minus square root 3 sine phi. And you also, of course, have to multiply by the strength of the interaction. And the eigenfunctions are also exactly known, and you use this to calculate the persistent current. What is a persistent current? Persistent current, as I said, is due to coherence, and so it depends on the off-diagonal element of the density operator. So you evolve the density operator in the Heisenberg form, starting from an arbitrary initial state. You raised your hand. And it turns out that the persistent current I1t is 4j over h bar, just factors outside, imaginary part of the e to the I phi times the expectation or the average value of the off-diagonal terms of the density operator if I want to calculate the current between the two bonds. So now since I have finished 10 minutes of my time, I'll tell you what the results are. So if you have no noise in the system, do this calculation exactly. Since you can diagonalize the Hamiltonian, you can calculate these time evolution operators, you calculate this exactly. What you'll find is that, interestingly, that you have a DC current, which is time independent. This is called the persistent current, plus oscillatory currents, which will oscillate with the eigenvalue differences of this Hamiltonian. What happens when you add noise? So the noise that we first did is a simple one. So I add noise. It's not just J, but J plus some zeta times this two-level jump process or the telegraph process. This is a simpler case because you can see your Hamiltonian actually commutes with itself at different times. And so if you diagonalize this Hamiltonian at one instant of time, it will remain diagonal, and you can solve this problem exactly. And interesting results that you find is that these oscillatory currents will actually decay to zero because of the stochastic noise, but the DC current persists. So you can actually retrieve quantum information starting from an arbitrary initial state, and that information retrieval is in fact reflected in the fact that there's also a persistent current despite decoherence due to the external noise. So, this is the first part. I don't have time in these 12 minutes to discuss the details of this calculation. Then the next case that I'm looking at is the one in which you actually add the noise, not here, but let's say to the side term, and that will complicate matters. For instance, if you have add a noise to, let's say the dot number 1, then you can see that this term actually does not commute with the unperturbed Hamiltonian. So now you have a situation in which H of T does not commute with itself at different times. So in the language of nuclear magnetic resonance, the first case is connected with what are called T1 processes. And now you also bring in T2 processes, transverse relaxation, and then the situation is a little more complicated because you have to really work with some dimensional matrices, and those calculations are still ongoing. Hopefully, I can report them next year. Thank you very much. This we have not looked at. I mean, if I go to I don't know the answer.
I mean, so that depends on the the kind of noise you put, I guess, right? So how does, I mean, like...
So you know, governed by a Poisson statistics, the probability that S such pulses occur in time t is like lambda t to the S divided by S factorial into minus lambda t, where lambda is the mean rate of these jumps that you introduce. So the lambda comes in, and also this eigenvalues of the Hamiltonian. It's a combination of. So you have the analogs of things like slow relaxation, rapid relaxation, motional narrowing that people in NMR talk about, and you have the analog of those time regimes all through, and you can see that very, very nicely. Exactly at this point, yeah. So it's like a tutorial model for discussing effects of coherence and also then effect of environmental noise and how you see decoherence and you can calculate decoherence exactly.